Imagine two people, Alice and Bob. They want to share a secret message like a password or a military code. But in between them lurks Eve, the eavesdropper, trying to intercept that message. In traditional cryptography, Alice would use mathematical encryption to scramble the message, and Bob would decrypt it using a key. The problem is simple but fatal. If Eve gets access to the key, the entire system collapses. Every encryption in classical computing, RSA, AES, or any modern cipher, relies on mathematical hardness. We assume that some problems, like factoring large prime numbers, are too complex for computers to solve in a reasonable time. But what happens when quantum computers become powerful enough to break those very assumptions? When a single quantum algorithm, like Shor's algorithm, can factor huge numbers millions of times faster than any classical computer, the foundation of modern digital security, bank transactions, military communications, online privacy, could crumble overnight. That's why physicists didn't just build quantum computers, they built quantum cryptography to defend against them. At its heart lies one stunning idea. Instead of relying on complex math to hide a secret, why not use the laws of nature themselves? Quantum cryptography uses the quantum properties of light particles, or photons, to create secure keys for encryption. And the most famous protocol that made this possible is called BB84, developed by Charles Bennett and Gilles Bressard in 1984. Here's how it works in simple terms. Alice wants to send Bob a secret encryption key made up of random bits, zeros and ones. But instead of sending electrical signals, she sends photons, each representing a 0 or 1 depending on its quantum polarization, the direction in which the light wave vibrates. Now, hear S the quantum twist. Each photon can be polarized either in one of two bases, let ES call them the rectilinear basis, plus, and the diagonal basis, X. In each basis, there are two possible polarizations, representing 0 and 1. For instance, in the plus basis, horizontal might mean 0, vertical means 1. In the X basis, 45-degree arc might mean 0, and 103 either means 1. Alice randomly chooses which basis to use for each photon she sends. Bob, on the other end, measures each incoming photon, but he doesn't know which basis Alice used, so he randomly guesses. Later, Alice and Bob publicly compare which bases they used, without revealing the actual bits. Whenever their bases match, they know their bits match too. The result? A shared sequence of bits, known as the quantum key, that both of them share, and no one else does. But here comes the most mind-blowing part. If Eve tries to intercept the photons in transit, quantum mechanics itself betrays her, because in quantum physics, the very act of measuring a particle changes its state. This is called the observer effect or wave function collapse. So when Eve measures the photons to spy, she inevitably alters their polarization. Later, when Bob receives them, his measurements no longer match Alice's expected results. The presence of Eve introduces errors, a telltale sign that the communication has been tampered with. It's like the universe whispering, "Someone is watching." This property, that information encoded in quantum states cannot be copied or measured without disturbance, is guaranteed by the Heisenberg uncertainty principle and the no-cloning theorem. These are not human-made rules. They're fundamental laws of reality. That's why quantum cryptography isn't just secure. It's physically unhackable. Now, let's understand what this means in the real world. Traditional encryption assumes that an attacker just doesn't have enough computational power. But quantum cryptography doesn't care how powerful the attacker is. Even with an infinite computer, you can't break it because you can't bypass physics. The most practical version of this technology today is called quantum key distribution, QKD. QKD doesn't transmit the actual message through quantum channels. Instead, it uses quantum mechanics to securely distribute encryption keys, which are then used for standard encrypted communication. Once the key is shared, Alice and Bob can communicate using conventional encryption, knowing that no one could have eavesdropped on the key exchange itself. Think of it as sending a padlock through a channel that explodes if anyone even looks at it. This technology isn't just theory, it's already being tested and used around the world. In 2017, China launched a satellite named Michius, the world's first quantum communication satellite. It beamed quantum keys between Beijing and Vienna, over 7,000 kilometers apart, proving that quantum encryption could work even in space. That was the birth of a quantum internet, an emerging vision where data across the planet travels securely through quantum channels, immune to interception. In 2020, the U.S. Department of Energy unveiled a National Quantum Internet Blueprint, aiming to connect quantum computers and secure nodes using QKD. The European Union, Japan, and Canada are racing along similar paths. Even tech giants like IBM, Toshiba, and ID Quantique are developing commercial quantum cryptography systems. Banks are starting to adopt QKD to protect financial transactions. Military networks are exploring it for command systems. And government communications are beginning to rely on it for the highest levels of secrecy. But like any emerging technology, quantum cryptography isn't perfect yet. For one, it's expensive and delicate. Quantum communication requires specialized hardware, single photon emitters, ultrasensitive detectors, and fiber optic lines that minimize photon loss. Current QKD systems can typically operate over a few hundred kilometers before the signal weakens. Another challenge is side-channel attacks, clever hacks that don't break quantum theory itself, but exploit loopholes in the devices. For instance, an attacker might shine bright light into a receiver to trick its detectors, or exploit imperfections in photon generation. So while the theory is unbreakable, the implementation still needs to be fortified. But scientists are already working on solutions, developing quantum repeaters that can extend communication range, device-independent QKD that verifies security regardless of hardware trust, and even entanglement-based cryptography, which takes the concept to another dimension altogether. Ah yes, entanglement. Perhaps the most hauntingly beautiful phenomenon in quantum mechanics. When two particles become entangled, they share a connection so deep that measuring one instantly determines the state of the other, no matter how far apart they are. It's as if the universe refuses to let them be independent. Einstein famously called it spooky action at a distance. In entanglement-based QKD, like the E91 protocol developed by Arthur Eckert, two distant users share pairs of entangled photons. Because their outcomes are perfectly correlated, they can generate identical keys without ever sending the key through any channel at all. If someone tries to intercept or measure the photons, the entanglement breaks, and again, the intrusion becomes instantly visible. This isn't just secure communication, it's communication enforced by the structure of reality itself. Now imagine what this could mean for the future. A world where governments, corporations, and individuals can exchange data that no hacker, no spy, not even a quantum supercomputer could ever decrypt. A future where the very fabric of nature guards our secrets. In this future, data theft might become obsolete. Election systems could become tamper-proof. Financial systems immune to cybercrime. Medical records beyond the reach of digital thieves. And global diplomacy carried out with absolute privacy. But with such power also comes a paradox. An unhackable network could protect truth, but also conceal lies. Nations could communicate without oversight. Criminals might hide under perfect secrecy. Quantum cryptography doesn't distinguish between moral and immoral use. It simply enforces the rule of nature. No unauthorized observation. So, as we build this quantum-secure world, we must also build the ethics to guide it. The most astonishing part of this story isn't just the science. It ewas the philosophy beneath it. For centuries, humanity believed that information could be copied infinitely, that messages could be intercepted, duplicated, or faked. But quantum mechanics shattered that illusion. It told us that information is physical. It's not abstract. It's woven into the state of particles themselves. When you measure a photon, you change it. When you copy a qubit, you violate nature's laws. In the quantum world, knowing something and disturbing it are the same thing. And from that strange truth, we built the possibility of perfect secrecy. So next time you hear the word unhackable, remember, it's not a promise from humans. It's a promise from the universe. Quantum cryptography isn't just a tool of cybersecurity. It's a glimpse into the deeper nature of reality, where even light itself conspires to protect information. From the mysterious laws that govern subatomic particles, humanity has forged a new kind of armor. One that doesn't rely on locks, codes, or firewalls, but on the very limits of existence itself. This isn't just technology. It's the beginning of a new era of communication, an era written not in code, but in quantum light. Because in the quantum world, truth cannot be stolen and secrets cannot be seen. That's not science fiction. That's quantum cryptography. Unhackable communication.